Yeah, so the last class we talked about two random variables and then extended to how to represent what we call it as probability distributions, joint probability distributions, and finally we looked towards the end, we looked at linear relationship between two random variables. That is what we call it as covariance, and we normalize it and we call it as correlation, and we can estimate the same from data as well, right. I mean you simply replace your expectation with summations that would average values no x bar, so that you could compute the correlation. So in fact our correlation, what we call it as nothing but x minus x bar into y minus y bar divided by n minus 1, I going from 1 to whatever, right. So this is our correlation, and I know this is covariance, we write it as x xy, this is covariance, and you know what is correlation, you normalize it with variance, standard deviation, square root of divided by square root of standard deviation of x into standard deviation of y will give me normalization. So the whole thing is actually correlation, we call it as R, yeah, square root of variance, sorry. Okay. And the theoretical way to do it is rho xy equals to expectation of x minus mu x into y minus mu y divided by again square root of variance of x into variance of y, right. This always lies between minus 1 to 1, right. So that is where we ended the class, right. So now the natural step after doing correlation is like, you know, what is the objective with which we started? We said single hypothesis, single variable, we said two variable independent. Now what is the next? Account for more variables and naturally account for interactions, dependencies, right. So now before I go into the more variables kind of, so how do I do for multiple variables? Correlation. This correlation is a very powerful concept. Suppose I have three variables x, y and z. How do I compute correlation? How do I compute correlation for three variables? Pairwise. So what is a compact way to represent, or what is a mathematical way to represent is the following. The diagonals are nothing but, what is the diagonals? Variance. I did not take a square root, okay. Sigma xx stands for variance, sigma xy is the covariance. This is called variance covariance matrix. Understand, this is a very powerful way of representing things, because as I told you, when you want to understand relationship among variables, okay, many variables, it will turn out to be a variance covariance matrix. To simply give you an idea how this can be useful, we all know about water networks, right. Water network that supplies water to the city. I want to find a leak in the water network. How do I do? I want to find a leak in the water network. How do I do? I want to know whether there is a leak or not. How do I do? Should I measure every line? Should I place sensor in every pipeline? That will be too expensive, right. You understand the problem? I want to monitor the water network for leaks, thefts, etc. Same with your power network, same with your gas pipelines. Today gas pipelines are also popular. In cities like Gujarat already, state like Gujarat already gas is in pipeline. Now I want to know whether there is a leak or theft. How do I do this, solve this? Where do I measure? Common sense, where do I measure? Huh? Joints, okay. Why? Why joints?
Because we can divide the pipelines in division
So you think joint is the only one which will get defective more?
No, whatever comes in it has to come out.
Between the joint, whatever there is.
Okay. What is an elegant way of doing? You are telling something. What is the elegant way of doing?
Maybe in and out of everything.
In and out of every pipe. Okay. What is that idea? We are looking for relationships. Inherently, we are looking for relationships. As I told you, a simple example is like F1 plus F2 equals to F3. It's a simple joint following it. Now, I know I have to measure only 2 because the third one is linearly related with the other 2, right. Now, if I know this covariance matrix, I kind of understand the relationship among all the variables, okay, of interest, and then I can pick those which are highly independent. The dependent variables can be neglected. In other words, if I do a rank of this matrix, if I get a full rank, what does it mean? So there is no point, but never, you will never have all the variables to be independent. That will tell you how many variables to measure. Of course, there will be noise, so there are elegant ways of doing it. We will not just look at the rank, we will look at the eigenvalues, etc. Okay, but the idea behind is to look for independent ones and strike out the dependent ones. Once I monitor only those few variables, then few measurements, I will be able to say whether there is a theft or leak under normal conditions versus abnormal conditions. I do not need to measure everywhere. This is the same idea used in your thumb impression. I think I told in this class, like earlier you used to take 6 months to 1 year, longer, today you rather, the idea is all your, if you treat every one of the pixel as a random variable, all your pixels are not independent. The rank of this covariance, variance, covariance matrix of your image is not going to be independent, there will be highly dependent, and therefore you need to pick up only those which are, you will not know which one is, in this example F1 plus F2 equals to F3, do you know which ones to save? You need to save only 2, you can do F1 F3, you can do F1 F2, or you could do F2 F3, but you will know what is the minimum number of variables that you need to store to get knowledge about the other ones. The same idea goes with your thumb impression, the same idea goes with your face images. When you talk about compression, what is compression doing? Data compression, same idea, explore relationships, identify those which are independent or minimum number of those which are independent, only use those. So image compression, data compression, all of this is based on this idea. Now I look at linear, if I extend it to non-linear, then you are talking about a bigger domain, but the fundamental idea is to look for relationships and pick up those which are minimal. So this is called sensor placement or sensor networks. This is where when we talk about sensor networks, where to place a sensor, this becomes very important. This kind of covariance variance matrix plays a major role in what I call our biomedical sensor placement or sensor networks, or what should I sense, what is the relationships in the data, right, how many are independent, how many are dependent, etc. Compression of data. So not just restricted to hypothesis testing or not just restricted to experiments, but it takes a long way. Whatever concepts you learn here are valid across, that is why it is important, right. So this is covariance variance matrix. If I move one step further, okay, this is covariance variance matrix. Do you all know about stock markets, right? Everybody knows stock markets. How many of you have played with it? Okay, good, I am happy, at least few are exploring. Okay, I was bit late, okay, but yes, stock market is something interesting for if you get into, right. At least the outcome I had is I get to know about the world, because if you know stock prices and if you know the rise and fall of stocks, then you get to know the world actually, okay, because that is the playground for the entire world. So you get to know all the news in the world and where investments happens, where everything goes on, right. So when you look at stocks, the Nifty price or your stock price, let us say TCS or whatever stock is, it evolves as a function of time. Now, the Nifty price today and 1 year before, will it have relationship? Very little. The Nifty price today and yesterday, will it have relationship? There is a time based relationship. So, if I make the same thing, okay, or in fact I could call what is okay. So, now I give it a time aspect, okay. I stand here and look at the relation with the past, okay. That becomes a function of time, that is used to evaluate relationships as a function of time. In biomedical, where will it be useful? Any idea? Treatment, okay. You cannot actually, you cannot do any biomedical signal processing without this, to be honest. This is called correlation covariance function. So, the first one is called cross covariance function, the below one is called auto covariance function, the relation of the signal with itself. This is where you look at your brain waves. If you put an ECG cap, the electrode here, the whatever measures, and the electrode behind whatever it measures, will they have relationship or not? The brain waves generating here and generating here, will they have relationship or not? Of course, there will be a time relationship, temporal relationship. Maybe the decision making task arises here first, animal instincts happen in the behind, and sometimes your animal instincts happen first and the waves propagate throughout, right. So, brain actually the waves propagate throughout the brain, right. That is why you have so many electrodes to measure your brain waves. Similarly, with your PQRS electrodes, I mean the electrodes to measure your PQRS, the ECG, because you know there is a sequence of activity in the heart and it is all time dependent. Something starts first, right, the pacemaker starts the clock, and then your aortic contraction followed by ventricular contraction, then blood pumping out, then your comes back deflation. There is a very sequence, time sequence, and there is a relationship as a function of time. So, these are all called time series, okay, and you can very well explore linear relationship in time as a function of time. That is what is I have written it here. Although we will not learn in this course, this is very important for you when you take home as a biomedical signal processing, or when you look at imaging anything, this is the first thing it will come to up, it is correlation. But now as a function of time, you are looking at what is the relation between this signal, current instant, and probably the past instant of this, because the signal would have propagated from here to frontal area or vice versa, right. And there is also a relationship of the signal with itself, like Nifty prices, current instant will depend upon past instants. There is a self relationship, that is the first one, which is called rho xx, which is called auto self relationship with itself as a function of past, and there is cross relationship between two signals where x and y are two random variables. Like as I said, the electrode wave here and here are the heart electrodes, like you place at 3 locations, right, you have a relationship, right. So, this is, so the correlation as a concept is not just a number, it extends as a matrix, it can also be extended to a function of time, okay. We will only look at correlation as a single number, but please do not underestimate correlation, the power of correlation. It extends to a matrix and it is also extends to a function to actually get you features, very important features and very important markers for analyzing. Make sense? So, with that note, we will move on to today what is called I am going to expand on the number of variables. Naturally, I will include the interaction slowly. Okay, right now we have the 2 variables, we have learned interactions. Now the next step is to include more variables and interactions. The first step of course is going to include more variables, and that is where we are going to do what is called as one-way ANOVA. Okay, I will tell you what is one-way, two-way, etc. Okay, we will first learn what is one-way ANOVA. The one-way ANOVA is, ANOVA stands for analysis of variance. Okay, so the one-way analysis of variance is to test the claim as given all the means are equal. So what is mu1, mu2, mu3, mu4? It could be in your biomedical sense. This could be different treatments for the same complication or same underlying disorder, right. So you have different treatments and you have the mean of the treatment, and you are assuming that, what are you assuming? None of them is different than the other, so all are equally useless. Okay, basically that is what you put, all are equally useless is your null hypothesis, and of course what do you want to do? You want to reject it. Okay, basically you want to say at least one method is working. Okay, that is what I intend to, but the first hypothesis is all are equally useless in treating the underlying complication. So that is my null hypothesis. Make sense? Okay. So this is an extension to what you can think of it as a 2 independent sample t-test. Of course later on I will add interactions as well. Okay, right now I have not added interactions, we will add interactions at a later point in the same idea. Okay, and in ANOVA there are some jargons, and this jargon is typically true for all kind of experimental designs. So you call something as response variable is the variable you are comparing. What is that? What is response variable? Typically is your outcome, the mean of the variable, that is the response variable. The mean of the response variable is what you are comparing. So the effect of treatment as the outcome is a y, and you want to test whether all mu y's are same, right. So mu y1, mu y2, mu y3, so the response variable is the variable you are comparing. Okay, and the factor variable, what is factor variable? Huh? What is it? So yes, exactly, the treatments or the factors that give rise to the output. So you are interested in output, and that output could be, so there are multiple treatments, right. So multiple treatments 1, 2, 3, 4, they are the factors. Okay, what is the response is the output. Typically y is your output, which is the response variable, and your factors x is your treatments, is your factors. Okay, and you can assume some small groups, and what we are going to do is we are going to try the, I will write down the hypothesis and later on. Okay. So the one way analysis we call it as one way because no, we will not get into this, do not worry about this, I will come back to this later when I teach you 2-way ANOVA. Okay. So let us not worry about why one way. What are the assumptions? Of course the assumptions are the data are equally sampled. Okay, that is an assumption, that is the same as your in t-test. Okay, but more importantly the key assumption here is the variances of each sample are assumed equal. So this is a big assumption. So what do I mean by, if I have n outcomes or n n outcomes, n samples, whatever I collect, all of them are normally distributed and have equal variance. So we will look at this in detail when I get into the math. Okay, these are the assumptions, the variances of each sample are assumed equal, the residuals are normally distributed, that is the noise is normally distributed. I will come to the model of ANOVA in short. Okay, I will explain just the overview and come to the math model. Okay, sorry. So let us go to the null hypothesis. The null hypothesis is that the means are all equal, all the means are equal, that is my null hypothesis. And the alternate hypothesis is what? At least one mean is different, at least one method is effective, so one mean is different, that is the alternate hypothesis. Okay. So, let us get into a simple example. Okay. So, let us say a salesman in cars sales want to find the difference between two types of cars in terms of mileage. Very simple idea, right? Two types of cars in terms of mileage. So, let us continue with the example. So, we want to find the difference between two cars in terms of mileage, right. This is a typical 2 sample t test could be done, right, because this is only 2 random variables. So, we have mid size vehicle and let us say a sports utility vehicle. Okay. Now, you will have what is the mean and the standard deviations, and we could do a pairwise t test. Okay. That is straightforward what we learnt. Okay. Now, if I want to say compare 3 vehicles, how do I do? Do I want to do pairwise? If I do pairwise, how many t tests I need to do? 3 tests, AB, BC, CA, right, and I will also have a confusion among them, right. So, it becomes really complicated, and it also does not nicely scale well. What do I mean by scale well? Suppose I want to have interactions, then the pairwise does not always help me for interactions, right, it does not scale well. Okay. So, that is where I want to develop a model or a method which will be able to compare many variables, also handle interactions. Okay. That is the idea, it has to scale well and it has to include interactions, clear. So, that is where we talk about ANOVA, it is used to compare multiple means, and difference between multiple means is significant or not significant is the question we are asking. Okay. And what is the difference? As I told you, you want to compare multiple, so t test will not be useful, and it is also a way to protect from excessive risk of type 1 error, meaning every time when you compare you will have AB, you will have a type 1 error of what, alpha is 0.01, and then again alpha equals to 0.1. What is the overall power of the test? You will not know, that becomes confounded. You see the point? If I have to compare 3 things and use 2 t test, AB you will have, BC you will have, CA you will have, what is the overall power of a test? Right, you have individual power of test, but what is the overall power of test, right? All of this becomes confounded, and that is the reason why you want to go for analysis of variance. Okay. So, here is a question we are asking, I am just setting up the stage. So, you have 3 populations, you do not know the individual means, you have taken the samples, you have the sample numbers, number of samples, you have the mean and you have the standard deviations, or you want to call it a sum square, whatever, right, variance and standard deviations you are given. Okay. With that, I want to see whether all 3 are equal or not equal. Is the stage clear? What we are trying to do, why are we doing, why not t test, etc. Clear?